My name is Joshua Hill. Most people know me as POSIX Ninja. Uh, Been around jailbreak scene for quite a while. So I basically taught myself everything about hacking, chief research between or for the green poison and absent jailbreak. Uh, so this is really more of a story about, well, my entire year of 2017. I was working on this exploit. I don't usually have that long of an attention span, but this was actually really, really fun to track. Uh, what got me started in this was actually back when I was a child. So I had an old Macintosh Performa. One other friend from school also had one. So we kind of shared, video games, etc. But when I was looking through mine one day, I discovered something called Apple Remote Access, which basically allows you to dial into another computer's phone and access that. This was 1997, of course. The internet was still very, very new. Honestly, I didn't have internet at this time. I did not even have a modem. I actually went to school and traded a Han Solo trading card game for my first 56K modem. Just to test this out. I dialed into his computer, set it up when he was in the shower one morning, and I made his novel a little better. So before this, there was a couple of odd things I've noticed when I was doing my research. For example, this kernel extension. As you can see, it has a copyright header at the top, but I'm not sure what they're copyrighting here because there's nothing there. This entire kernel extension, every single one of those files is empty. So after a while, you kind of got to think, like, is this a common pattern? So I basically pulled every single Apple open source code, extracted them, line counted every single one, sorted it in descending order, and then I checked to see which ones were empty and which projects had the most number of empty files. One of them was an old friend of mine, a VPN agent. Originally, first discovered this file when I was trying to look into it. I couldn't tell why it was redacted. Going back and looking into the binary, there was a key. It was called no sandbox. Looking into what that key does, it basically redirected it around the sandbox initialization. I wonder why I didn't want people to find that. Yeah, it's clearly blatant security to obscurity. A lot of repeat offenders were showing up. UI user kit, a lot. Of course, the main one we're interested in was the PPP one. Very, very old software. I actually found the source code for it on one of the Apple vintage websites. Unfortunately, Apple removed Stuffit Expander support, so I could not look at it. But yeah, so then I realized, okay, so the entire VPN system is actually built on this old legacy modem support. It makes sense. They both do similar things, but one just does it over sound waves, the other one does it over a network. So how do I actually get in and start installing these PPP configurations and VPN stuff to actually test it? There's one thing which kind of bothered me always. Whenever you go up to change your Wi-Fi password or different network or your DNS, it never asks you for your root password. This stuff is held in very secure locations. Something has to be running as root there. The easiest method I found was simply go up to your network configuration files. You can select one, hit export configuration, and it basically exports a plist file containing all the different settings for the network configuration. You can actually modify that and add some extra ones in there which don't really document. This was mostly just for testing though. So beyond that, we have to, well, the VPN stuff runs as the user. So we still need to get a little more higher privileges. So looking around through there, I discovered there was still a Unix socket in /var/run called PTP config-d. It was 777 world readable writable executable. So let's see what can be done. This is the basic header format for the packets going over the Unix socket. Very simple protocol. One thing that caught my attention, I first thought that would be the bug, is you see down where it says off the very bottom, UCHAR and data 1. They should not have a character or an array of size 1 there. The entire structure is now going to be offset by 7 bytes. If you look inside the code, you see Apple tries to fix this a couple times. They first make a macro, which basically just subtracts 1 from it before parsing it. They still did that wrong. So in the code, they continually to call that and then fix that. Yeah, so these are some of the commands you can send to it. Most of them, well, I wasn't sure which one to focus on, so I just focused on them all. Basically, very simple fuzzy. But there was really only one thing that stood out to me. Oh yeah, lots of other options. So, a little bit more about modems. Since this exploit actually did require a modem to be set up as a network device, most people don't have modems anymore. I've had a hard time trying to acquire one myself. But yeah, modems were extremely complicated back then. Every single provider, they actually have their own unique specific, well, they still do today. Basebands are pretty awful. But Apple needed a way to support all these people. Unfortunately, you don't necessarily need a modem in order to do this. So on the older Macs, every single time you plugged in a serial to USB adapter, it would automatically create a new serial line network configuration in there. Most of the serial line modems, or well, since the modems are also serial line, it's very easy to simply modify what type it is. You can turn any serial line device into a modem. Later on, when they released the newer MacBook Pros, they actually, well, it has USB-C, so you can't really plug up a serial line USB device to it. Fortunately, every single adapter, USB-C to A I found, would automatically create a serial line device for that adapter. So if you had used USB, you didn't even need to have a modem. So, this isn't quite the fuzzer script, but this is the exploit for the privilege escalation. Even though I fuzzed everything in here continuously. The stupidest bug I found was this one right here, the Syn PPP Connect. Apparently, if you run it from this socket, it launches PPP as root, but not as a user. So when I was fuzzing it, these are typically the error codes it should have been. Starting at 256, down a little bit. This is the error result my fuzzer got. And here you can see, it actually took me a while because I kept fuzzing it and not realizing what was happening. Then I finally realized, oh, it's actually launching a root, not user anymore. So now that we can actually get PPP running as the root user, how do we actually gain code execution from that? So back in 1997, Apple released their iMac G3, and it included a built-in modem. One of the first computers made specifically for the internet, iMac, Internet Mac, and they included different modem stuff, the CCL scripts. Apple documented it quite well on their webpage. So, and these scripts handle both calling up and answering other telephones. So what's in a typical CCL bundle? It's really just a folder with an info list and a CCL script. It's an example of, well, this is my info list. And you can probably start to get at where I'm going on the next slide. Simply adding a whole bunch of A's and a couple little bytes into there. It actually allows you to set specific variables inside of the bundle, including username, password, the APN. Oh yeah, and you can set a couple variable ones also. So those variable strings were kind of the first thing I tested. I spent about 2 days working on something to fuzz or create CCL scripts so I could fuzz it all. And I thought, you know what, let's just try these variable string things in there. Instant success. But, well, I actually tried it with a bunch of the commands, and it turns out half of them were broken. And here's where it starts getting weird. The variable strings are actually Pascal strings. So it actually makes it a little more difficult. We can't just overwrite the null value and then, you know, read in some arbitrary data after that. So it's still quite interesting. I've never seen a Pascal string buffer overflow in my life. So here's the first one. And note, and the third is just a bar string. I'm telling it to put bar string 27, 27 together. Both of those contain 255 A bytes. This is basically a classic buffer overflow, but with modern protections, pick the stack quickly and it fails. Max string is almost exactly the same. And finally, write was also a good one. This one was actually the one I decided to focus on because it seemed a lot more fun. So this is a very simple example of a CCL script. All this does is basically sets a label. It looks similar to assembly code. Set a label at the top, increment number of tries by 1, write hello world, create a new label, check to see if the number of tries is greater than 5. If it is, jump to 3. Otherwise, jump back to 1, increment again. It'll print hello world 5 times. These are all the different commands we get in there. A lot of these are interesting, but they kind of all come into play once you're trying to create this proof of concept export script. I'll go through some of the more interesting ones. So my first idea was, how about the note one? If I can somehow grab the stack cookie earlier in memory, then there'd be no problem just rewriting that, and then next the instruction plan. But that seems kind of boring. The interesting one was slightly more difficult because it had more constraints. These are the basic gadgets I have to work with. The return command is essentially a limited 16-bit read to the script. Well, it's almost. I'll get to that later. JSR, 16-bit write, some timing controls. We can almost create a full Turing-based machine just on this information alone. So here's some of the code. So you can see here, it says SB top of stack. If it's equal to the maximum top of stack, then do this. If not, it doesn't think what a top of stack is greater or less than. And I want to point out that during the write overflow, we can overwrite the SV top of stack and the SV script on it. Oh, and SV stack. So we control the stack and the top of stack. So very nice, pretty read primitive, almost. Other gadgets. So we can actually memory compare. Say we want to try and find, where our memory is allocated in space. We can actually compare the bytes there with one we have in a variable string. So we can actually find where our code is at. Of course, saw the if tries and increment tries earlier. Easily to use for loops, conditionals. I was also thinking it could be used as to store flags for this Turing machine, but might be going a little too deep. Oh yes, and we can also have the different states, like when it's answered, or when it call started. Yeah, just between these two, we should be able to exploit it, right? Fortunately, there's a couple of pitfalls involved in this. So the maximum size of the script is 32 kilobytes. That is 32 kilobytes of characters or 32 kilobytes of lines, whichever comes first. So we're limited to those reads as either under 0x7 FFFF, and we can only write 0x7 FFF. And the way it works, it's all based on the line number again. So one issue with this, it means if you want to write the value 0x20 to place at its offset, you would have to be at line 32 in the script. Which also means you cannot read or write the same byte. It also means that unfortunately you cannot write to stack because you cannot create those addresses. Or you cannot also get gadgets from the dynamic linker, because those are too far in memory. But where we end up overflowing starts at, where is it at? String buffer here, 256. So everything below that we can overwrite. The stack, top of stack, right buffer. Interesting thing about this is nesting limit is only 16, but it was defined as a integer. So they're literally indexing 32 bits inside of a 16 array integer or array. But there's some other fun stuff we can actually overwrite beyond that. One of my personal favorite is G null string down there. So I can change the value of null. Null is defined as a Pascal string consisting of 1 byte. That 1 byte is a space, 0x20. But since we can overwrite this, we can actually also use it as a scratch register. If you look at how it gets the bar strings, if the string is greater than the max number of strings, it just returns that G null string we can overwrite. So as far as how to exploit this, in CC Engine's tight loop, it basically is constantly generating these callout structures. You see, it's basically just a linked list which contains other callout structures to be executed in order. Almost better than ROP. But part of the problem is actually figuring out where in memory these things are coming allocated, because it's in a very tight loop. Luckily, though, we can actually delay the script a bit by adding a character delay. Because back in the day, modems were really, really slow. Well, they were slow by today's standards, but by their standards, they were really, really fast. So they had to go really, really slowly to send it sometimes. It gives you a little bit more time and control on the key. So, finally, persistence. This one was actually kind of a freebie. So it includes a resource file for PPP. So if you just create this .ppp.rc in your home directory, it will automatically launch a shell script for you whenever the PPP comes online. Oh, yeah, for the to execute those routes, you have to use the etc, but it's probably protected by SIP. So, but however, you still need the code execution for the persistent one. Right? However, fortunately, Apple actually ships Netcat by default, and also Netcat, EC version at least, can access Unix sockets. A very simple echo string of bytes to PPP conf.d, and they're using Apple's own signed programs to trigger this exploit. Yeah, but since Apple doesn't usually pay up on Mac OS X bugs, I eventually just shared this with them out of good faith. We've been working on the VPN application. They might not feel comfortable with importing all these VPN bugs. So it was same reporting, but built up a little bit of a reputation with them over the years. Finally got it into the App Store as the very first VPN firewall that was definitely not easy. But this is only a scratch on the surface of the number of bugs in there. This was the path of least resistance. There were other ones which looked like command injections, quite a few more. It's a very, very old portion of code, and I think very few people even understand it. However, you can't really have a VPN security product if the VPN on the phone is broken. So, really hoping that more people will start looking into this. So, yeah, we're doing some amazing things. The App Guardian or Guardian app should be out. So, officially out of beta next month. And some other amazing things in the pipeline we're working on. Should be a good future. And that's about it.